Paint program open.
Was this the first example that you wrote?
Yeah, the grades I think were.
See?
Yeah. Yeah.
If I were to submit an assignment like this, would it be an issue? The page break did not work, so.
I think it should be okay. They just care about that it's, you know, signed, so it should be okay. Right, yeah.
The page break disappeared. There were times.
There's something wrong with it set up, yeah.
The
It
table
looks
disappeared.
like you have the print size set wrong. It's too small.
The table disappeared. The font changed.
That's okay. Quite frankly, I don't care. So you can sit down.
But I thought, you know, as a teacher, you would know what another teacher would do.
Ah, well, it's EAP, isn't it?
Isn't it? I include everything. It's just the structures somewhat.
I don't know how many marks there are for structure, to be honest. I know for me, I might take 1 or 2% off. But yeah, it's not going to kill you or anything, you know. Right. I'll just see. Celine? Yes. Okay. Chidera? Okay, still no. Mohamed? Yeah, now. Sabrina? Sabrina C? No. Moza? Ahmed?
Yes.
I didn't get your name when I called it the first time.
I was 12 minutes late.
No. Okay, hang on. Safra? No. 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 Mahmoud?
Here.
Zara? Mo?
Yeah.
Daniel? Sabrina? Amna? No. Amjad, where are you going? We're about to start.
I just want to get something from
5 minutes, where are you going? Why did you wait until the very end to go?
No, I don't want to get into them.
No, but I mean, why did you wait until I'm about to start the second class to go? Like, you could have gone 5 minutes ago, and you'd be...
5 minutes.
No, I'm starting now.
After the class? After the...
Yeah. Your coursework is not printed, is it?
No.
Go. Go quickly. Quickly. I don't know what to make of this class sometimes.
So this is the list, I think, on the left one.
Has everybody signed this who wants to go to RCSI on the 26th? Yes? So I'm going to give this list to Tiago after class. Okay. Now, listen, Ahmed, I'm speaking. Thank you. Mahmoud, Gafar, I'm speaking here. Can I have your attention, please? Thank you. Yes, I have everybody's attention, including Autumn. You're listening? Thank you. So look. Barry, come on. Come on, sit down. Thank you. Now just the thing about the attendance. So, is anyone coming in? No. I'm just responding to feedback from the class that I think some people would like the class to be a little bit more punctual at the start. So that's fine. But if the class is going to be a little bit more punctual at the start, then I can't have people coming in 11/12 minutes late, you know, because it really hinders the start. If I'm mindful of the fact that as I'm talking that there could be people still trailing in. So, but it's not a problem I have, you know. So if we're going to be a little bit sharper about we are starting class now, then I need to be a little bit sharper about the attendance, okay? So for today, I'll mark those late people in as present, okay? But in future, if I call your name and you're not here to say I'm here, and you didn't tell a friend to tell me, oh, I went to the bathroom or whatever, then I'll just have to mark you absent then, okay? And if you're so late, like 15 minutes late, then I'll just not let the student in, okay? I'm just responding to feedback, that's all. You understand? So that's it's not particularly what I want to be doing, but that's life, I suppose. Okay, so we'll continue now. Expectation and variance. Right, so we're just building on what we did in the last lesson, which is probability tables, and they'll form a big part of what we're doing in this lesson. So we'll just start off with a little example here. We'll keep it easy and just make it two outcomes. X and P. We'll keep it very easy actually. Win and lose. And we'll say win is, yeah, we'll keep it as easy as possible. 0.5 and 0.5 then, for win and lose. Now, let's say in this game, if you lose, that doesn't cost you anything. It costs you €0. And if you win, let's keep it easy. Let's say that means you get €1. Okay. If you play the game once, how much do you expect to win or lose? Well, it's not really clear if you play the game once, because you'll either win or you lose. But if I say to you, okay, you play the game 100 times, how often do you expect to win? 50 times. And how much do you win when you win? €1. So for playing 100 times, that corresponds to winning how much money? 50 euros. Okay, so if you play one time, that corresponds to winning how much? 50 cents. Now this is quite interesting, because if you play the game once, you can never win 50 cents, right? Because your possibilities are either you win nothing or you win €1. But it's useful. It's useful to think about it as if you could win 50 cents each time. Even though we know that each time you can only win €1 or nothing. So that's why I really want to say it's as if you could win 50 cents per turn. So the reason I'm doing this is I want to give you just an understanding of the word expectation. When we talk about the expectation, we're talking about a number that represents a sort of average. Per turn, how much are you expected to win? You're expected to win 50 cents per turn. Do you actually win 50 cents per turn? No. But it's very useful to think about it this way. You expect to win 50 cents per turn. Because this gives you a way to know how much to charge to play this game. If I was running this game, for me, I should charge more than 50 cents to play per turn. At least 50 cents. Right? Because if I charge less than 50 cents, then you are paying me less than 50 cents to win 50 cents per turn. Do you get the kind of the logic here? Yeah? No. What's confusing? Yeah. So if I charge you 40 cents to play this game, how much do you expect to win? 50 cents, we said, per turn. And you paid 40 cents per turn. So you are up 10 cent profit. This is bad for me running the game. I should charge you 60 cents to play. Do you understand? Yeah. So I always, on average, get 10 cents per turn. Yeah?
So why would anyone pay more to play than the prize?
Because people are idiots. That's what we've learned. That's what we've learned from the active listening. This is irrational. Exactly right. Why would you play when you're expected to lose? But people do this all the time, you know. Huh? The arcade, yeah. So you're right, though. This gives us the idea of what we call a fair. And fair represents if your expectation, which we use the letter E, if the expectation is 0. Now you might say, why is this fair if you expect to win nothing and lose nothing? It's fair for everyone. So if I charge you 50 cents to play, then I don't make any money, but neither do you. It's a fair game. So mathematically, fair has a precise meaning here. Fair means the expectation is 0. Okay, so that's something you should note. Now we'll look at more complicated examples in a moment. This is very easy. But suppose I ask you, how could we quickly calculate this 50 cent here? How could we quickly calculate it? Well, what you could do is you take the probability and you multiply it by its value. You take the probability and you multiply it by its value, and you add this up. This actually is the definition of expected value. The expected value is the total of all the probabilities multiplied by all their values. So let's have a look at a harder example. Can I scroll down a little bit? Like, let's say we have a more complicated game. You roll a die, and we'll keep it easy. We'll say the probabilities are 1 out of 6 for each. Okay, so let's say in this game, if you get a 1, a 2, or a 3, no, we'll say if we get a 1, you don't win anything. And let's imagine you had to pay €1 to play. So this is €1 to play. So if you get a 1, you win nothing. So your outcome is -1, isn't it? If you paid €1 and you win nothing, then overall you've lost €1. Okay? If you get a 2 or a 3, you get your money back. You get your euro back. So what would be the value of these outcomes? 0. Okay? If you get a 4, you get paid out €2. So if someone pays you €2, but you had to pay €1 to play, what's your net position? You're gaining €1 if you get a 4 or a 5. And we'll say 6 is the jackpot. So if you get a 6, let's say you get paid €11. So what's your position here? You're up €10. So I want to know, if you play this game, what is the expected outcome? How much money do you expect to make or lose? Now, I think the answer will be positive, so you should be making money in this game. So, the calculation is you multiply the value of the outcomes by their probabilities and add them all up. So the first one is -1 times 1/6, plus 0, plus 0, plus what's the next one? 1/6 plus 1/6 plus 10 times 1/6. Okay, so what's this here? Now, because expectation is a value, in this case a money value, let's make it a 2 decimal place number. So what would that be? What is it? 1.88. 1.83. So what does that mean? On average, each time you play, you are gaining €1.83 on average, okay? Right, can I Continue now. Move down. Yeah. Scroll down. How many numbers are on a roulette wheel? Does anyone know?
24.
No, it's more than 24. Isn't it?
Yeah.
It's like 39, 40 or something?
Yeah, there is. Google.
Quick Google. How many numbers on a roulette wheel? It's an odd. It starts at 00 and goes up to what? Got an answer?
0 to 36.
0 to 36. Perfect.
18 of which are red.
Yeah, 18 red, 18 black, and 1 white. Okay. I think we got it there, Mo. Thank you.
All numbers are red. Even.
Odds are reds, evens are blacks, zeros white.
Yeah.
Okay.
You said it was a zero. You said it was a number.
Yeah, well, 00. So there's 37 slots on the roulette wheel. So each of these are over 37. Okay, so I'll draw the roulette wheel here. Well, I won't really, but the way the roulette wheel works is that it switches between red and black all the way around, okay? There are 18 red, 18 black, and there's one here which is white. So the rules of roulette are quite simple. You pick a colour. So you say red. If you get red, you double your money. So you put €5 on red. If you get red, then you get back €10. If you get the wrong colour, then you lose your money that you bet. And if it lands on white, everybody loses. So there's a 1 in 37 chance that nobody at the table wins. Okay? So what I want you to do, and let's say you place bets in values of €5. So to play, you must put down a €5 chip.
What if both people bet that?
Oh yeah, so both people, they double their money. So if I bet €5 on red and you bet €5 on red, then I get €10 and you get €10 then. Yeah. Right, so what I want you to do is to complete this one here will say is win. This one is lose, and this one is lose. And the difference between these two, it's really the same thing as far as you're concerned. No, actually, you know what? I will make it just 2. Let's just make it a bit simpler. You can keep it as 3 if you like. The last box is everybody loses, but you only care about if you lose, not if your friends lose. Right, so win and lose. Okay. So let's fill this out together. What is your position if you pick the right colour and you win? So how much money do you get? So remember, you have to pay €5. So in total you get €5. Yeah. So you're positive 5. Right? And what's your position if you guess the wrong colour between red and black? Negative 5. Now what is your probability of winning here? 18 over 37. And of losing? Yeah, because you have the extra losing square. Alright, so I want you to calculate what is the expected outcome for this game here for you. Yeah, now remember it's money, so I needed 2 decimal places. Minus 1.14 cent. Yeah. You got that? Yeah? It's 5 times 18 over 37 minus 5 times 19 over 37. By the way, this is the best game at the casino. It's the only game where you can only lose 14 cents per turn. All the other games you lose more. So actually this is the best position you could have. Each turn makes you lose 14 cents. So believe it or not, this is the best game at the casino. But still, each time you play, it's like you're given 14 cents to the casino on average per turn. Yeah? Okay.
So why do people play it?
Huh?
We figured out the
Irrationality, yeah. Yeah.
That's all I'm doing.
I don't really know why people play casinos, because to me it seems like in the long run your position is only ever to lose. You know? Yeah.
You know how can you can mathematically rate like bets and stuff?
Yeah.
Like, while you're playing like
Yeah.
cards, or can you do that in roulette?
Can't do that in roulette. There's some possibility in cards, like 21, to keep track of the cards dealt, so you can know when's the best time to play or not. But the way the casinos prevent that is they often use a large number of decks. So some casinos might use as many as 6 decks. So when you have 6 decks, it means that counting has little advantage, because so what if you know that 2 kings have been played? You know, if there was only 1 deck, then you know that there's 2 kings left. But if there's 6 decks, then yeah, it has very little benefit then. It has very little benefit then.
A mathematician never gonna be a gambler.
No, that's not true. That's not true. Sometimes I bet on horses, and I do find often I win more than I lose. But the reason for that is I often have an advantage because I know people who run the stables, and they sometimes give me a little tip. You know, because sometimes if you're a manager of a stable, you might know that particular week a particular horse is running better than expected. Perhaps they have a little bit of extra energy or something. Or perhaps some of the other horses are a little bit sick. So you sometimes might think, you know what, actually, I think it's a good week for so-and-so. So the only time it's rational to bet is if you have extra information that the other people don't. You know? But this is the same thing that happens in investments, you know. Like when you invest in a company, I'm trying to give you some valuable financial lessons here, okay? When you invest in a company, it is a type of bet. If you invest in Apple, you're betting that their values would increase, okay? You might say there's not much difference between that and betting on a horse. The people who succeed are the same people who succeed at betting on horses. They have extra information that the common person doesn't. So perhaps some people say, no, don't bet on Apple because I've learned from a friend on the inside that they're releasing a new phone and apparently it's terrible and it's coming out next month. Yeah. Or imagine that you're inside Apple and imagine you discover that they're releasing a product next week and it's a surprise release that people don't know about. So it will be in your interest to buy those shares, because often when Apple releases a product and perhaps it's a success and it's a surprise release, you know, you see a little increase in the price of the share, you know. Now you're not allowed to do this. You're not supposed to have this information, but you know, secrets get out. This is the only rational time now to do this. Okay, so the next thing we have to do is variance. Yeah?
You would advise us not to invest in stock?
No, I just say if you invest, you should have extra information. Information that perhaps is not publicly known would be the best way to do it. You know? Okay, variance next. Yeah, Mahmood, I'd give 2 advices. If you're going to invest, you either should know something about the company, or if you invest, you should hold on to it for a long time. Okay, because in the long run, investments do pay off. But
So what would you invest in if not stock or gambling?
well, first you need money to invest, which I do not have. So, variance. Now, if we look at these 2 tables here, okay, so let's say we have X and P. x and p. So let's say here we have 0 and 2, and this is a half, and this is a half. Okay, and here we have 0 and 3, and this is a third, and this is 2/3. Can you calculate each expectation here, please? Is it? Oh, sorry, I made a mistake here. I meant here 1, and this one here, sorry, is 2. Yeah. 1 and 1. Yeah. Now, each time you play, what's your expected position? To be up 1 unit of value. Okay? But we can see that each of these games are quite different. In the first game, what's your chances of going home with nothing? 50-50, yeah. And in the second game? 2 out of 3. However, in the first game, you could go home with 2, potentially, and in the second game, you could go home with 3. Now, which game you prefer? Well, if you were playing the game 100 times, it doesn't really matter, because after 100 attempts, in both situations, how much would you be up? 100 units if you play 100 times, because each time you're up 1 unit. Okay, but imagine you could only play this game once, one shot only. Which would you pick? Now, before you answer, I'd actually like to see what people's choices would be. So you can play the first game on the left here once, or you can play the game on the right once. And just to remind you, in this game you have 50-50 chance of going home with nothing or going home with €2. In this game here you have 2 out of 3 chance of going home with nothing, but a 1 in 3 chance of going home with a little bit more, which is €3. So who would opt for the first game on the left? Okay, and the other game? Okay, so the people here are taking a bit more risk. You're willing to take a higher risk of going home with nothing, so you could have a little bit extra. This is just personal preference. It's called, like how sensitive you are to risk, how tolerant you are of risk. So this game is more conservative than this game. But we need a way to measure that, because we can't see that in the expectation, right? Because in both expectations it's the same. So this gives us our next idea called variance. It represents how much the outcome could vary. It's a little bit like standard deviation. Remember, standard deviation represents a sort of a spread of data. So the definition of variance will look remarkably like standard deviation. It's the expected value squared. It's the how much you expect to get by squaring the values minus the normal expectation squared on the outside. Doesn't this look awfully similar to standard deviation? It effectively is, except there's no square root. That's one difference. There's no square root. So it's a little bit like, it's like variance equals sigma squared. It's like this. Can you see the difference here? I'll calculate as an example. So if you want to write this down. So let's calculate the first one. So for the first game, the variance, right, so we're looking at x squared. So it's 0 squared times a half plus 2 squared times a half minus, and what did we say this was? Did you calculate the expected value to be? 1 squared. So this would be 4 over 2 is 2 minus 1, 1. The variance here would be 0 squared times 2 over 3 plus 3 squared times 1 over 3 minus 1 squared. So what would that be? That would be 6 minus No? Oh, 9 over 3 is 3. 3 minus 1, which is 2. So the variance is twice as much in the second game than the first game. Yeah. Okay, so these are two good examples if you want to just write that down. Yeah. Yeah, that's this part of the formula. Because they were 1 we calculated earlier. So the answer is telling us that both games, on average, you expect to win the same amount of money, but the second game has a greater range of outcomes. So, like, imagine you played this game 3 times. What's the best you could do in the first game? The absolute best you could do is you get €6 in the first game. In the second game, if you played 3 times, for example, what's the best you could possibly get? €9. Now, that's actually quite different. So if you play this game 3 times, you could be up as much as 6 or as much as 9. So the 2 on the right represents a greater variance of possibilities in the second game. Now, you might say, what's the interpretation? So variance doesn't really have much of an interpretation, but the square root of it does. So if I just scroll down a little bit, square root of 1 and square root of 2. So here this is still 1, and here this is 1.4. So what you're saying here is, in the first game, you expect to win €1 per turn, plus or minus €1 on average. So you're kind of somewhere between 0 and 2. Well, we knew that already, because you could win 0 and you could win 2 on average. Whereas here, what you're saying is, you could still win 1, plus or minus 1.4. Now, that doesn't make too much sense for just one game, because you know you can't lose money here. But when you play it 100 times, it makes more sense. So if you play this game 100 times, you could win €100 plus or minus €100. Kind of the same here. This is, you're asking me what does it mean? It doesn't really have a direct interpretation at this level. It's just a way to measure how much variability there is. A rough interpretation is the square root of it represents how much your outcomes could swing by, just roughly. Yeah, but it's not very accurate here, because I think because my numbers are so close together. If we had bigger numbers and different outcomes, it would make a little bit more sense. Okay, anyways, we're not going to worry too much about that. Okay, can I scroll down? Yeah? Okay. Let's see, let's do another one here. So, okay. Right. I guess another good example, maybe to tie it in with the active listening, you know. Okay. All right, I want to think of an example here. We'll imagine an example. So, let's take a person who buys, or let's say, I know. You know those health clinics, like, you know, I don't know, you go to the clinic and they realign your energy or something, some nonsense like that, you know, or they put crystals on you and you know what I'm talking about, so revitalize your energy and get your center realigned or something like this, okay? So you might think, what's the harm in going to something like this, you know? Well, you've got 2 possibilities here. You either go or you don't go. So let's have a look at the outcomes here. If you go, what's your net position? Well, you obviously have to pay to go, so there's some actual money here, okay?
This is not sensible.
A calculation, okay? So let's say outcomes here and probabilities here. But I suppose what I'm saying is, if you go, obviously you have to pay money. But what's the alternative? The alternative is you don't go. But if you're the type of person who doesn't go, then you're also the type of person that's more likely to go to the GP. So like, for example, if you're the type of person that goes to one of these clinics, then you're the type of person who feels like they don't need modern Western medicine. And so they're less likely to go to the GP. So you might think, well, what's the cost in that? Well, if you are going to the GP more often, even if it's just for something small like a cold, then there's a small chance that the GP could pick up something very serious that wasn't the main reason you went in for. So let's try and put some numbers on that. So what is the probability you think the GP will pick up something serious that wasn't your intention of going to the GP? So like maybe you just went to the GP for, you have a cold, and then the GP is checking you out and they said, oh, actually, hang on, your blood pressure is a little bit high. Maybe we should get a scan or something. How often do you think that might happen? Like, what number will we put down?
1 in 1,000.
1 in 1,000? It might even be better than that.
1 in 10.
No.
Let's say, make 1%, we'll say. Okay, 1%. Okay, and 0.99 then. Yeah? So, do you think that's a good thing or a bad thing here if the GP picks up something? It's a good thing because, otherwise you're going untreated. Now, it's difficult because it's money, but let me put it this way. How much money would you put on that? Like, imagine you want to put a value on the GP discovering something serious 6 months sooner because you went to the GP more often. How much money would you have put to that? If I said to you, how much money do you value getting a diagnosis of cancer 6 months sooner than you would have?
1,000 euros.
1,000 euros, that seems like a good number to me. 1,000 euros, okay? What's the worst that would happen if you went to the GP? Well, you went to the GP says you have a cold, stay home and drink tea. You kind of feel like your 50 euros was lost because you said, well, I could have done that myself. I didn't need the GP to tell me. So I'd say here you would have a minus 50 then. Okay? Now, calculate here the expected value, please. So what's the expected value of the GP visit? What is it? Positive or negative? Positive. Do you understand? Positive. So each visit to the GP, it's like you're gaining 50 euros, although you're paying 50 euros. The problem is you don't realise it because when you actually win, it happens so rarely. I don't know if this example is too weird, but I wanted to tie it into the active listening. Yeah? Yeah? Does this example make sense? Guys, there's lots of people moving around and it's wrecking my head. Okay, just sit down, please. Pretend like I'm trying to expand your mind. Okay? Can you understand what's happening in this example here? Now, some people might even value it more than 1,000 euros. Because getting a diagnosis 6 months sooner because you visit the GP more often, I would maybe value that at more than 1,000 euros. Maybe 2,000, 3,000, whatever. Okay? But my thing is, this is an example. It's more rational to go to the GP. What's the alternative? Or you go to the health clinic. You get your energy realigned. Okay? So, there's really only two possibilities here. You pay 50 euros, and your outcome is you lose 50 euros, or that's it. Okay, there's only one possibility. You pay 50 euros and you lose 50 euros. Why is there only one possibility? Because the person who realigns your energy is never going to notice that lump on your back when they're doing they're not a medical professional. So, here you can be up 50 euros and here you can be down 50 euros. Do you get what I'm saying? Like, it's totally irrational here. Anyways, we can also see this in the variance. So, what's the variance in the first one? Can we calculate that? And then calculate the variance in the second one. We'll write down, what was the expected value here, Angela? 50.5, and this one here is minus 50. Okay, so give me the variance here. Is it? Well, whatever it is. You got that? What's the first one? Guys, you got the first one? What is it? What's the first answer? It should be 1,000 squared times 0.01 minus 50 squared. Well, actually, sorry. It's plus minus 50 squared times 0.99 minus 50.5, was it? What do you get here? Come on, guys, what you got here? Don't keep me waiting. 1. 992. Okay, so roughly 1,000, in other words, roughly. And what is it here? 0. You calculate it. You know? There's no variance. And that makes sense, because there's only one thing that can happen here. You lose 50 euros. So, the variance is always between 0 and infinity, where 0 represents no variation in the outcomes. And the bigger the number, the more variation in the outcome. Would you agree there's a big variation here? There's a big variation from being told you have cancer and go home and drink tea. Okay, so there's a big variation here. All right. So anyways, I just want to finish this example by saying high variance can hide the expected outcome. If the variance is very high, it's hard to see what you expect to get per turn. Okay, so for the last few minutes there, let's see. Let's have a look here. Yeah, these are okay. These are okay. You definitely need to be able to do 1 to 6 for the exam. If you're having trouble doing those, it's a problem. Yeah. All right, if you want to get started on those now, please.